Welcome, everyone. Thank you for joining us today at the Berkeley CDAR Risk Seminar. Today, I am delighted to have David Ritzwoller joining us, his co-author. Joseph Romano is also here in the audience on a topic that I think, as many of you know, has been dear to my heart for a few years now. So the title is Uncertainty in the Hot Hand Fallacy: Detecting Streaky Alternatives to Random Bernoulli Sequences. And David, I'll hand off to you. So please go ahead.
Fantastic. Okay. Thank you very much for having me. Yeah, okay, so let's get started. Oh yeah, and please interrupt me if there are any questions or if I haven't seen anything in the chat or anything like that. Okay, so I'm going to start by posing what would seem to be a relatively simple problem. Suppose that we observe S Bernoulli sequences, each of length n, and that we're interested in testing the null hypothesis that these sequences are IID against the alternative that they're stationary but potentially dependent. As it turns out, the interpretation of tests of this form have been pivotal in the development of behavioral economics. In particular, in the early 1970s, Amos Tversky and Daniel Kahneman developed a theory of how humans misperceive randomness that they call belief in the law of small numbers. And the idea here is that people find small samples to be overly representative of the essential characteristics of a sample. And that just is to say that people find, people sort of are overconfident in the strength of the conclusions that they can reach from small samples. And an example that they emphasize in their initial discussion of this theory is the design of experiments in academic social sciences. So they interview a sample of psychologists and they ask them questions about how large a sample would need to be in order to achieve a certain statistical power against a reasonable alternative. And they find that for even people that have maybe some formal training in statistics, that our intuitive notions of what we can learn from a sample are overconfident. And this theory that people are overconfident in either recent information or in small samples has been very influential in behavioral economics and finance. And what you should think of here is that when we want to model how people perceive asset prices, people see an increase in asset prices, they're going to find that increase to be overly representative of the dynamics of that asset and invest. And so these ideas have contributed to sort of standard textbook models in behavioral economics and finance.
Quick question. Has any work been done relating this formal finding to the tremendous affection that people seem to have for anecdotal evidence in the field?
So I'm not an expert on the behavioral economics literature. I do know that this sort of storytelling and the relationship between storytelling and investor behavior is something that Nick Bloom at Stanford's economics department is working on right now, and something that Robert Schiller has worked on pretty extensively. But I'm not an expert in that literature, so I can't point to a particular paper or anything like this.
Statisticians have the celebrated quip that the plural of anecdote is not data, and that quip wouldn't be necessary if it didn't correct a popular misperception.
Yes. Okay, so the hot hand fallacy is a behavioral bias attributable to the belief in the law of small numbers. And it'll be broadly the subject of our talk today. So the idea here is that that the hot hand fallacy refers to people's tendency to perceive streaks of consecutive successes as overly representative of positive dependence. So when you perceive a streak, in a sequence, you're going to overestimate the dependence in that sequence. And this sort of cognitive fallacy was initially posed and investigated empirically in a paper by Gvt, Vallone, and Tversky in the mid-'80s, where they studied the particular context of the hot hand in basketball. So what they do is they document that people have very strong beliefs that basketball players get the hot hand, that when you're making a lot of basketball shots, the probability that you're going to make your next shot is higher than it would be otherwise. And they documented this belief among coaches and players and fans, and argued that that this people believe that there's a really sizable dependence in basketball shooting. However, and by contrast, they then implemented a sort of an experiment where they had around 30 players from Cornell's men's and women's basketball teams shoot 100 shots in a row. And when they analyzed the sequences of shot outcomes, they failed to reject the null hypothesis that these shot outcomes were IID. And sort of this contrast that this empirical finding that basketball shooting, the conclusion that basketball shooting is IID, was very provocative, and it was so surprising to people that it became very, very influential and became, in a lot of ways, a key piece of empirical support for the broader theories of belief in the law of small numbers and the behavioral economics that Amos Tversky and Daniel Kahneman developed. And so this result, that basketball shooting is IID, but that we believe that there's a lot of dependence, we believe fallaciously that there's a lot of dependence, became the academic consensus for the following 3 decades. And it's, like I said, it's sort of the central piece of empirical support in popular presentations of these theories in Daniel Kahneman's 2011 book, Thinking Fast and Slow, for example. So a couple of years ago, Joshua Miller and Adam Sanjirho challenged the original Gvt results. They identified a subtle, significant second-order bias in the hypothesis tests that Gvt implemented. And when they revisited the Gvt shooting data, but corrected for this bias, they argued that the Gvt results are reversed, that they uncovered critical flaws sufficient to not only invalidate the most compelling evidence against the hot hand, but even to vindicate the belief in streakiness. And in a more conservative interpretation of their findings, resulted in persisting uncertainty in the behavioral economics community about the empirical support for the hot hand fallacy. Dan Benjamin, in a recent Handbook of Behavioral Economics article, says that these new analyses reopens but does not answer the key question of whether there is a hot hand bias, a belief in a stronger hot hand than there really is. So our objective is to clarify and quantify the uncertainty in the evidence that basketball shooting experiments have contributed to our understanding of the hot hand fallacy. So we're going to develop a formal statistical framework for testing the randomness of a set of Bernoulli sequences. We're going to emphasize the practical and conceptual distinctions between individual, joint, and multiple hypothesis tests. We're then going to measure the finite sample power of these hypothesis tests with a local asymptotic approximation. And equipped with these tools, we're going to provide a comprehensive reanalysis of the existing evidence from controlled basketball shooting experiments. Okay, so in this talk, I'm going to try to move a little bit achronologically relative to the paper, sort of interweaving how we formalize the problem, the theory we develop to address the problem, and then our reanalysis of the data. And towards that end, and then sort of to fix ideas, I'm going to briefly describe the empirical context of these controlled basketball shooting experiments. Okay, so these controlled basketball shooting experiments, including the original Gvt shooting experiment, are situations in which basketball players are observed taking a sequence of incentivized shots under identical conditions. And in our analysis, we're going to focus on the GVT shooting experiment, partially because the data are publicly available, but also because the results from the GVT and Miller and Sinherho analyses of these data are starkly different and have driven both the former consensus in the empirical support for the hot hand fallacy and the current uncertainty. And so the GVT experiment consists of the shooting sequences of 100 shots for 26 members of Cornell's men's and women's varsity and junior varsity basketball teams. Miller and Sinherho in their econometrica paper, and then some additional preprints analyze some additional experiments, including their own. We will at some points discuss the design and results of these experiments, but we won't. Our reanalysis of the data will be confined to the GVT experiment. Okay, so I'm going to begin by defining some notation and posing the formal problem that we're considering. So our data consist of the shooting sequences for S shooters, each of which shoots n consecutive shots. X sub I is going to denote the vector of outcomes for shooter I, and X will denote the matrix of outcomes for all shooters. So these are Bernoulli trials, 1 denoting a made shot and 0 denoting a missed shot. And the question of interest in this literature is whether these sequences of trials are independent and identically distributed. In this, there are 3 types of testing problems that we can query. The first is the strongest question, which is, are all of these, sort of the joint null hypothesis, are all of these shooting sequences IID? So is X sub I IID for each shooter? And in contrast, we could also ask whether an individual shooter is IID, and I'm going to denote that null hypothesis by H not I, where this joint null hypothesis is the intersection of these individual null hypotheses. And given a collection of shooting sequences, if you would like to query which of the null hypotheses you can reject, this consists of the multiple hypothesis testing problem, wherein you test each of the individual null hypotheses simultaneously and ask which of them you can reject. And throughout our analysis, we're going to maintain that the alternatives are stationary. They follow a stationary Bernoulli PI sequence. So PI is the marginal success rate, where this sort of capital P denotes the process, and capital PI denotes the process, and capital P denotes the collection of processes. And we're going to be testing these null hypotheses against what we describe as streaky alternatives. And these will, because not all alternatives to IID shooting are consistent with people's notions of the hot hand, of what it would mean to have the hot hand in shooting. And in these alternatives will consist of processes where the parameters theta kp and theta kd are greater than 0 for some integer k. So what are these? Theta bar kp and theta bar kd are averages over shooters of the individual parameters theta kp and theta kd, where theta kp is the probability of a success, probability of a made shot following k consecutive successes, minus the unconditional probability of success. And theta kd is the probability of success following k consecutive successes, minus the probability of success following k consecutive misses. And so the idea here is that we're not trying to take a stance on what it means for someone to have the hot hand, but we're just trying to fix a class of alternatives that are consistent with most notions of what it would mean to deviate from randomness in basketball shooting.
Can I ask a question right here?
Yeah.
So that this simplest part of your term, the PI of Xij equals 1, you're taking a sample average to get an unconditional probability. Is that right?
So these are PI of.
I-
So these are parameters. These are functionals of the underlying process. So these are the parameters that we're interested in that could be large. What we're going to do in order to test these null hypotheses is simply put hats on these parameters. So we're going to consider, yes, so we're going to consider the test statistics.
Mhm.
So the sort of we're putting a hat on theta kp is
Mhm.
going to be the statistic p hat nk, which is the proportion of makes after k consecutive makes. And likewise, d hat nk is the proportion of makes after k consecutive makes minus the proportion of makes after k consecutive misses. Now, it's important to note the structure of these parameters. So if you think about it for a minute, what you would do if you're computing this proportion is you're taking the total number of streaks of length k plus 1 and dividing it by the total number of streaks of length k. That just, if we want to compute the proportion of makes after k consecutive makes, because if you're a streak of length k plus 1, you must have been a streak of length k, and we need to know the proportion of streaks of length k that turn into streaks of length k plus 1. And likewise for this d hat k. And so these statistics take the form of sums of overlapping sequences. And so when we want to analyze the asymptotics of these statistics, we're going to need to take account for this dependence. And also these statistics p bar k and d bar k are just the averages of these statistics over shooters and correspond to these joint statistics theta bar p and theta bar d.
Got it. Thanks.
Okay, so I'm going to start out for the first half of the talk by discussing the practical challenges in analyzing these data, and then I'm going to give an implementation of these tests, and that's going to help pose why we're interested in developing some theory of the asymptotic behavior of some of our statistics of interest. Okay, so suppose that we would like to identify which shooters deviate from randomness, and that is to say we're interested in doing the multiple hypothesis testing problem, where we assess which of the individual level hypotheses we can reject. In general, the probability of a false rejection of at least one of the individual null hypotheses increases rapidly with S. So for example, suppose S was equal to 10, there were 10 shooters, and all of the null hypotheses were true, and we're performing some hypothesis test at level 0.05, at level exactly 0.05, then the probability of at least one false rejection is approximately 0.4, and this will grow rapidly with S. So our goal, therefore, will be to control the family-wise error rate, i.e. the probability of at least one false rejection. And we do this by implementing standard multiple inference or multiple testing procedures. And in particular, we implement a step-down procedure with Sadat critical values, which can be shown to be optimal in sort of a maximum sense for our problem, where the hypotheses are independent across shooters. Okay. So the second empirical challenge when considering problems of this form is the finite sample bias, developed studied by Miller and Sinherholt. So to fix ideas, our first result is a characterization of the asymptotics of these statistics under the null hypothesis. So under the null hypothesis H dot I, the statistics p hat nk and d hat nk are asymptotically normal with mean 0, and variances sigma squared p and sigma squared d given by these expressions. And so even for this statement, we need to apply an appropriate central limit theorem that accounts for the dependence in the structure of our statistics of interest. Okay, so so this is sort of an asymptotic approximation to the sampling distributions of our statistics. How then does this perform in finite sampling? So what we've done here is we've done a Monte Carlo analysis where we take 100,000 draws of Bernoulli 1/2 random variables of length 100. And over each of these draws, we take the expectation, we take the average of the realizations of our statistics of interest over these 100,000 draws. And what we find is that the finite sample expectation of these statistics decreases rapidly with k. So for d hat 4 k with k equals 4, the expectation is close to minus 0.18. So there's a really substantial second order bias in these statistics. And so if you would sort of a natural first approach to trying to test our null hypotheses of interest would be to compare the realization of the statistic to, say, the 0.95 quantile of their asymptotic distributions, while that procedure has a type 1 error rate that, again, is below the nominal level of 0.05 and decreases rapidly with k. And what Miller and Sanhiro try to argue is that when you try to correct for these biases, the results of the original analyses are reversed and are sensitive to this bias, in fact. And what they do to correct, and the types of procedures that we study in our analysis, are permutation tests. So permutation tests automatically account for the finite sample biases in a statistic. So how permutation tests work: suppose that we are considering any statistic Tn, where this could be p hat k or d hat k. The permutation distribution of this statistic is this term r hat Tn. And what you do to compute the permutation distribution, you consider every permutation of your data set. So you have your data set xi, and you permute it a whole bunch of times, and you compute your statistic of interest on each of these permuted copies of your data set. You then the distribution of the realizations of your statistic of interest on these permuted copies of your data set is a permutation distribution. And how permutation tests work: they reject at level alpha if the realization of your statistic is greater than the 1 minus alpha quantile of the permutation distribution. Now, it's well known that in finite samples, permutation tests control the type 1 error rate exactly under the null hypothesis, but what might be less known is that, in fact, permutation tests are the only tests that control the type 1 error rate exactly under the null hypothesis. And then there's a similar procedure that we study for the joint test statistics, and all you do here is you permute these sequences independently for each shooter and still compute the distribution of the realizations of those statistics across shooters. Okay. But we're also interested in trying to gauge how much dependence there is in our data, and that task of estimation will also be subject to these small sample biases. So if we consider the permutation distribution for a statistic Tn, the mean of the permutation distribution, so if we take the average of the realizations of our statistic of interest, Tn, over all of the permutations in the data set, we're going to denote that by eta hat. Under the null hypothesis, the expectation of this term will be exactly equal to the expectation of Tnx. And so this suggests the bias-corrected estimators for our parameters of interest, theta p and then theta d, where what we do is we just add this bias correction term to the to our standard statistics of interest. And when we do that, we're going to add a tilde notation, and we can do the same when we average these statistics over shooters. Okay, so we've outlined the standard ways of approaching this problem, and let's try to see sort of the challenges when we try to analyze this problem. Let's see what happens when we implement these on the data from the original Gvt Experiment Tversky paper. So this table reports the p-values of the joint tests of the joint null hypothesis H naught using p bar k and d bar k. And what we find is that so for k equals 1, we don't really, there isn't evidence, there isn't strong evidence against this null hypothesis. There is a rejection at the 5% level at k equals 2, and again at k equals 3, where there's a little bit, the evidence is a little bit stronger for k equals 3 with d, and then some mixed evidence with k equals 4. And then so this is where we're querying, is there any evidence against randomness in this data set at all? If we would like to identify which shooters deviate from randomness, what we find by performing a multiple hypothesis testing procedure, what we find is that there's only strong evidence that we only reject the null hypothesis H naught I for one shooter consistently. So for k equals 1 to 3. And when we look at the realizations of this shooter shooting sequence, we find it's sort of remarkably streaky. The shooter identified in our data as shooter 109 starts out by missing 10 shots in a row, and then they make 15 shots in a row, and they miss a lot, and make a lot. And it's pretty plain that this is not variation that you could reasonably expect to occur from a random Bernoulli sequence, even if you're taking even if you're taking looking at the best performing, the most streaky sequence in 26 draws. And in fact, this figure gives the permutation distribution for the statistic d hat for k equals 1. And the vertical black line displays the realization of d hat 1 for this shooter. So the p-value for the permutation test is the proportion of permutations, realizations of that are to the right of this statistic of this the vertical black line, and the p-value here is something like 0.0001. So there's strong evidence against the null hypothesis that this shooting sequence is random. But when we go back to the original data set and gauge what happens, the strength of the evidence against streaky shooting in the data without this shooter, we find that the rejection of the null is no longer present. So I believe this figure displays the permutation distributions for the joint statistics p bar k for k equals 1, 2, 3, and 4. The permutation distribution is this gradient here, and the observed statistic is the vertical black line, and the vertical blue line gives the 95th quantile of the permutation distribution. So when we include shooter 109 in the sample, when we include shooter 109 in the sample, we see we're rejecting these tests at the 5% level, but without shooter 109, the rejection of these tests is no longer at least true at the 5% level, and for larger and smaller values of k is no longer even close to significant. And this similar results hold for the D statistic that compares streaks of makes to streaks of misses. Okay, so this is what you can learn from this data from these statistics, and similar procedures are reported in Miller and Sinherho. An attempting conclusion that you could reach from this analysis is that streakiness is confined to a small number of players in basketball shooting, that maybe there's heterogeneity in how streaky basketball players are, that maybe there's a small number of shooters with very hot hands. So we argue that, by contrast, that the deviation from randomness exhibited by shooter 109 is unlikely to be indicative of what could realistically be expected from even a small proportion of basketball shooters. So for just sort of a quick sketch of that argument, if we look at the realizations of these bias-corrected statistics for shooter 109, the realization for D tilde is about 0.379. So what that's saying is that the probability of success, or the probability of a make, empirically for this shooter is 37% higher after a make than a miss. And if we try to give that some context, this figure displays the field goal, a histogram of the field goal percentages for NBA players in, I believe, the 2018-2019 season. And we can see the dispersion in this data is on the order of order of 20%. So if shooter 109 is a realistic estimate for how streaky some shooters could be, then that would be equivalent to saying that you're going back and forth between shooting like the best player in the NBA and shooting like the worst player in the NBA after making and missing a shot.
Can I ask a question?
Yes.
So is it possible that shooter 109 was deliberately confounding the experiment? This is a really great shooter who decided to, miss some streaks.
I absolutely. So I think we interpret shooter 109 as an outlier. That I think we can surmise fairly, and what we're arguing is that the shooting sequence for this shooter is non-IID, that can be concluded with some strength, which is something that what was not the claim that the data in this experiment taken at face value are IID was something that was accepted and argued pretty forcefully in the literature for many years. But I think it's absolutely fair to sort of probe this experiment, whether there would be some room for whether we should believe this data. Certainly, what I'm saying here is that if we take this estimate of how much streakiness at face value, it would imply a sort of an amount of variation within player of how your field goal percentage that wouldn't seem realistic relative to the dispersion in field goal percentages across players. But moreover, what we're going to argue is that existing controlled shooting experiments do not have sufficient power to detect what would be realistic alternatives. So what we're going to argue there is that the evidence from this experiment do not have sufficient power to make a strong argument that there is or is not large deviations from randomness in basketball shooting. And in order to do that, we need a way of approximating, of first understanding the procedures that we're implementing and then approximating their performance both under the null and under alternatives. And so as we're studying permutation tests, that means we need to, so our goal is to approximate the power of the permutation tests that we apply. And our approach will be to characterize the asymptotic behavior of these permutation distributions. So our first result is to start, we can characterize the behavior of these distributions under the null. So we find that under the null, the permutation distribution for the statistic d bar nk and t hat nk and p hat nk, the permutation distributions are asymptotically normal with mean 0 and variance sigma t, where t is equal to d or p depending on the statistic that you're analyzing. And so what that's saying is that the asymptotic distribution of the permutation distribution converges to the same distribution that the statistics do asymptotically. And if you want, in order to show a result of this form, what you do is you verify something called Hofting's condition, which means that you need to argue that the statistics, so if we want to characterize the permutation distribution for the statistic Tn, you need to argue that root n Tn and root n Tn capital pi are asymptotically independent, where this expression xi capital pi indicates that we've randomly permuted this data. So there's the set of permutations of 1 to n, and we've chosen a random realization of that. And so the approach that we develop is, and this is complicated in our setting, again, because the statistics that we consider have this dependence. And so what we do is we begin by conditioning on the permutation that's realized. And this allows us to apply an appropriate central limit theorem developed by Charles Stein for dependent random variables. Now, of course, this asymptotic independence isn't going to hold for every permutation. So for example, the identity permutation that just keeps the sequence the same. But we show that we formulate a condition under which about the permutation under which the asymptotic independence will hold, and show that this condition holds with probability 1 as n goes to infinity. Okay, so we've shown that we've characterized the behavior of these distributions under the null hypothesis. And in order to measure their power, we're going to have to characterize their behavior under alternatives. So if we consider the statistic t hat n1, so the statistic d n1 for simplicity, and we let a hat n denote the number of ones in the first n elements of x, then if this expression here, root n to the 1/2 a hat n minus n pi, converges in distribution to some limiting distribution, then the permutation distribution for d hat n1 will be asymptotically normal, is asymptotically normal. So again, what we're finding here is that the permutation distributions for these statistics, even under this broad class of general alternatives, converge in distribution to the same distributions that the corresponding statistics do asymptotically. Okay, and this argument is a little bit more subtle, and our approach will be to first consider non-random sequences. So let's suppose that ln h is the permutation distribution for our statistic of interest based on an1s, where h is given by this normalized and centered expression. We show that if we consider this deterministic sequence, hn converging to h, i.e. this expression converges, this normalized expression converges to h, then the permutation distribution, which in this sort of fixed framework is not a random object, converges in distribution to normal 0, 1. And then, so after we've shown this, we've shown that this convergence holds for fixed sequences of realizations, and then we can use that result with an appeal to the almost sure representation theorem to complete the proof that this convergence holds for these random, possibly dependent alternatives. Okay, so what we've done is we've characterized the behavior of the permutation distributions that compose the tests that we study, both under the null and under alternatives. And what we're going to do is we're going to use that result to measure the power of the tests that we're interested in against streaky alternatives. And in order to do that, we need to develop sort of a stylized model of what streaky alternatives are that can sort of, we would like to, that we argue have given upper bound to the type of dependence that you could be interested in, realistically be interested in detecting in the data that we study. Okay, so the particular model that we study is, suppose there are S individuals, each associated with a Bernoulli sequence, each associated with a Bernoulli sequence of length n, and that of these S individuals can be divided into two types, random and streaky. The random types are IID, Bernoulli, PI, and this, whereas the streaky types, after a streak of M1s, the probability that they make a shot increases by epsilon, and the probability, and additionally, the probability that they make a shot decreases by epsilon after a streak of M0s. So in this model, each individual is streaky with probability zeta. And so that is, we're assuming that the number of individuals in our model that are streaky is binomial S zeta. Okay. And in our analysis, we're going to specialize to the case that every player's marginal probability of success is 0.5, partially because it does a good job of modeling our data, but also because it simplifies some of the analysis. Okay, so we have two core results. Mostly, so the power of the permutation test of the individual null hypothesis, H naught I, i.e. the hypothesis that individual I is random against the alternative that individual I is streaky, where epsilon is equal to H over root n. So this is a local perturbation, converges to this expression. So 1 minus the CDF of the 1 minus alpha normal quantile minus this constant phi, which depends on the statistic that you're studying, as well as k, which depends on the statistic that you're studying, m, which if you recall is the how many makes until streaky individuals, their probability of success increases by epsilon, and then h, which is the magnitude of the deviation from randomness. And then a straightforward corollary of this result is that the power of the sort of the test of the joint test, H naught, against the alternative where there are binomial S zeta streaky individuals and the magnitude of the deviation from randomness is epsilon, is given by this expression where we've just introduced this the term zeta is introduced after this constant. Okay, so the constant is a little subtle, but here's a table of its values for the case of D for small k and m. And what you can do with this result is it allows you to approximate the finite sample power of your tests. So suppose you're interested in testing against a given value of epsilon, and you know the size of your sample well, and you want to have and you know the size of your sample. Well, that pins down a value of h, and so then you can introduce those into this constant, and that solves for the power. So, for example, suppose you're using the statistic d bar 1, then you would like to have a power of beta. This is the expression for what the product n, the sample size, the length of a sequence for individuals, and s, how many individuals would need to be in order to have power beta. Okay, so we've developed this sort of asymptotic approximation to the power of statistics. How does this perform in practice? So here, this figure reports the results of a Monte Carlo study where we measure here we're measuring the power of individual tests of the hypothesis H naught I for statistics D hat and K. And what we're finding is that the straight line gives the power of these tests measured with simulation, and the dotted line gives our asymptotic approximation to the power. And so what we find is that this approximation works surprisingly accurately, particularly over the range of epsilon that we're investigating, at least in the simulation. If we're interested in analyzing the power for the joint tests using, in this case, the statistic D bar 1, this figure reports the results of another Monte Carlo experiment where we compute the power of this test with simulation at each point over a grid of different values of zeta and epsilon, and report the blocked colored regions report sort of contours of the power surface of these Monte Carlo measurements, and these gray dotted lines report our asymptotic approximation to the contours of that surface. And again, what we find is that our asymptotic approximation is quite accurate for sample sizes that we're interested in investigating. Okay, so we've developed a method for approximating the power of the tests that we're interested in against this sort of stylized alternative. And we would like to use this to assess the strength, the power of the power of the tests that are being implemented in this literature on the hot hand fallacy. And in order to do that, we need to give some guidance as to how much deviation from randomness could reasonably be expected in this data. So suppose very roughly that the marginal shooting percentage for all shooters is 50%. And that for half of the shooters, so for zeta equals 0.5, shooting percentage increases and decreases by half of the interquartile range of the distribution of field goal percentages of NBA players after making their previous M shots or missing the previous M shots. So we're going to assume that for 50% of the players, so was there a question?
Yeah, can I ask a question? So
yeah.
I'm trying to understand the underlying model behind the alternative. So is it that, let's suppose M is 3, is it that if I make one shot, there's no effect? If I make 2 shots, there's no effect. But if I then make the 3rd shot, suddenly I switch into a different state. And then how do I switch back? As soon as I
miss a shot,
have a failure, I switch back to the regular state.
Exactly.
Yeah, sorry. So I'm trying to think about that model as opposed to one where maybe I gradually get there. So if I make 1, there's a little bit of information. If I make 2, there's a little bit more. If I make 3, then we've got more, which would seem to be more natural as an underlying model of the phenomenon.
I think that's a fair assessment. Yeah.
Okay. Yeah. So you've chosen to do this particular Markov switching model as an alternative because your methods allow you to do it. I guess that's more or less correct?
Well, so if the concern is that we're not, there could be something that's happening at k equals 1, and that after one shot and that this is not accumulating, if we're only allowing this to kick in at larger sequences, well, why not consider the model where m equals 1? So That is, you make a shot. After you make one shot, your probability of success. After you make one shot, your probability of success goes up by some amount and stays elevated. Now, if you tell me any model where in the interim you make one shot, it goes up by some amount, another shot it goes up by another amount, and another shot it goes up by a larger amount, the power against that alternative is going to be bounded from above by the power against this alternative with m equals 1 and just a larger value of this parameter epsilon. So we're still, what we're trying to do, so we can do that. We can bound any sort of, any deviation below. But it is of specific interest in this literature that deviations, to detect against deviations from randomness that begin only after streaks of makes, because some theories for the underlying process consist of that there is sort of a causal effect of the make itself, of the streak itself, on on sort of the probability of success. And even more broadly, our goal is not to try to pose a model of what it means by the hot hand. It's just to provide sort of a goalpost.
Okay. Thank you.
Okay. So with that in mind, what we're trying to do here is we're going to try to provide an upper bound for how much variation you could reasonably expect there to be in the model. So for this, in this case that I'm outlining here, m is equal. We're just saying I'm giving an argument for particular values of epsilon and zeta. So we're going to say, okay, say 50% of the shooters go by this model, and epsilon corresponds to going back and forth between the 75th percentile and the 25th percentile of the distribution of NBA players after making M shots and missing M shots. And that's a pretty large deviation. So we're going to argue that's an upper bound, and also consider some relaxations. What if it's only 25%, or what if it's you go back between the 66th and 33rd percentiles. Now the literature on the subject highlights m equals 3 as of substantive interest, because they're interested in engaging the effect of that there's a change in regime brought on by making 3 shots. And so we're going to keep that in mind, although I'm going to report the results for different values of k and m. Okay, so this figure reports the power curves for 4 experiments that people have looked at in this literature. The different curves give different values of k and m. So the purple curve gives the upper bound, and the blue curve is k equal 3, which is the sort of alternatives and statistics that have been identified as of interest in this literature. The vertical, this column gives zeta equals 0.5, so 50% of the players are streaky on average, and this player gives sort of a relaxation of that upper bound. 25% of the players are streaky on average. The dot dash line gives you're moving back and forth between the 25th and the 75th percentile. The dotted line gives the alternative, where you're moving back and forth between the 33rd and 66th percentile. So for the GVT experiment, particularly for k equals 3, we can see that these tests are pretty radically underpowered. For k equals 3, the power is something like 15%. And even for k equals 1, at our most conservative upper bound, the power is only something like 0.6. For Miller and Sanherho run a slightly larger experiment that if you do believe that half of the players are moving back and forth between at the 25th and 75th percentiles of a distribution, then you could make a case. We think that is still that's still a very strong upper bound, or very, so that's a strong upper bound, and that it's sort of even weak relaxations to that upper bound, a smaller proportion of players having the hot hand, or being streaky, or a smaller or sort of a weaker value of streakiness, it's still going to be pretty heavily underpowered, particularly for alternatives in which deviations, or let's say the bulk of a deviation, occurs after a longer streak. Okay. Are there any questions about this? Okay. So let's try to characterize what we've learned. So our argument is that existing randomized shooting experiments are insufficiently powered to detect deviations from randomness consistent with realistic parameterizations of positive dependence in basketball shooting. And as a result, they're unable to provide an informative estimate of the mean or dispersion of the serial dependence in basketball shooting. This could be challenged by a strong or robust rejection of the joint null hypothesis, but at least in the case of the Gvt experiment, rejection of the joint null hypothesis is sensitive to the inclusion of an outlier, and this is broadly consistent with the evidence from the other experiments that are run where there are some outlying individuals in particular. And so this result cuts both ways. For many years, it was argued that the evidence against IID shooting, the evidence against streaky shooting in this data was conclusive support that basketball shooting is random. It's not, and that these evidence are conclusive that there's streakiness in basketball shooting. Our results do not support that conclusion. And it brings to mind the original motivation for Kahneman and Tversky's original motivation for believers in the law of small numbers, that empirical scientists tend to overestimate how much they can learn from small sample sizes. Okay, and a last note on this literature is that the goal of this literature, at least as it pertains to behavioral economics, should be to provide a test of the hot hand fallacy rather than just the hot hand. And what we argue is that what you would like to do in this situation is to compare estimates of the deviation from randomness in your data with audiences' expectations of that deviation from randomness. And in our manuscript, we provide a review of the evidence on beliefs, so expectations in these deviations from randomness, and conclude that the existing evidence is not directly comparable to any estimates of our parameters of interest. And so we suggest an alternative design that relies on eliciting probabilistic expectations from an experimental audience, asking the observer of a shooter to record the expectation of a probability that the shooter makes their next shot, rather than just whether or not they make their next shot. And this can be, there are incentive schemes that are compatible with this design. Okay, and to conclude, again, our objective has been to clarify and quantify the uncertainty in the empirical support for the tendency to perceive streaks as overly representative of positive dependence. We conclude that substantially larger data sets are required for informative estimates of the streakiness in basketball shooting. When we reject IID shooting consistently for only one participant in the Gvt shooting experiment, providing strong evidence, if taken at face value, that basketball shooting is not perfectly random, but that the evidence against randomness is limited to that player in that sample. And we would like to argue that future research should directly test the accuracy of predictions of streakiness in stochastic processes as a direct test of the hot hand fallacy. Thank you. Are there any follow-up questions?
I have a technical question. Your analysis depends heavily on the permutation tests, and permutations grow in size pretty quickly with the size of the underlying data set. Are there computational techniques to manage the increases in computational time? And as a follow-up question, are there studies about how representative a subset of permutations can be determined in order to get reasonably close to the same statistical results that you get with the full permutation set?
Yes, absolutely. We don't, I omitted this from the slides, but even when we're considering a streak of 100, we're not considering it taking all 100 factorial permutations.
Good.
We take a sample. You randomly sample permutations. It's like when you do a bootstrap.
Okay.
You don't consider all. You sample from it. And there's been a lot of work on characterizing the accuracy of a permutation test for when you're considering only a subset of the permutations. This line of literature was more active in the 80s and 90s, where our computational constraints were tighter. These days, in these cases, I'm doing something like 100,000 permutations, and the residual error there is pretty low. I'm doing a pretty accurate job of computing the permutation distribution.
I think there is some literature on the quality of different sampling methodologies. I know Kelly Ottoboni and Philip Stark have worked on this. So have you looked at different sampling methodologies? I don't know whether you're doing them homegrown or taking stuff off the shelf.
So we haven't, and Joe is the expert on this, but our conclusion was that simply taking uniform draws from the set of permutations with a very large number of permutations, a very large number of draws rather, was leaving the order of error that's remaining is negligible. That was our conclusion in this case, because we do have our computational resources were large enough that we didn't feel that was a first order concern. What does happen, however, is these are 100 ones and zeros, so the permutation distribution still is going to be a very discrete object. In order for a permutation distribution to be exact, you would need to randomize the test. So we don't randomize the test, but that is for small data settings. So if this would have been streaks of length 10, say, then not randomizing would have induced a considerable degree of conservativeness. But our conclusion was that, again, for streaks of length 100, we weren't, the amount of conservative that we were introducing into our procedures was not considerable, and would not be substantively impacting the results.
Thank you. Do we have more questions?
Hi, David. I have a question. Very nice talk.
Thank you.
So for the inference point of view, can we construct like confidence interval for the next shooting for a player? Yeah,
exactly. So we don't do that, but we give some recommendations for how that would be done. So what you would want to do is a procedure. Let me see if I can find what this is called. It's not.
Sure.
sorry, 1 second. Okay, so sorry. So it would be called, so there's a set of general bootstrap methods for stationary time series. And these would be called the moving blocks bootstrap, the stationary bootstrap, or their general subsampling could work for this as well. And so we give some cites for that in section 5.4 of our paper. And if you're interested in these questions on how would we do confidence intervals for sort of dependent time series, it's an interesting literature, and I would start with those references.
Great, thank you.
Great.
I have one more question, and I apologize that it's not as well posed perhaps as would be ideal. You've looked at very carefully at the likelihood of getting the degree of streakiness that's observed has been observed in practice in various rigorous ways. Another approach might be to understand what kind of distributions of streakiness among individuals, power laws, for example, or others, would result in the level of streakiness that's been seen. And I wonder if any work has been done on that.
I think that's a very interesting question. It's not something that work along those lines is not something that I'm aware of. I think people have made a sort of simulation type arguments about the type of Markov switching models that we consider, but analyzing theoretically models more rich than what we'd consider would be involved, but I think would be pretty interesting. Again, I think there needs to be the empirical context would need to be scaled up in order to discriminate even between sort of subtle forms of dependence that we might be interested in.
Thank you.
Any more questions? Okay, well, David, thank you for a super clear and interesting talk. Really loved it.
Great.
And we'll definitely be in touch to follow up. Can we post your slides and your paper on our website?
Yeah, that's no problem. Thanks. I've sent the archive link. I'll go ahead and attach my slides. And thanks so much for having me.
Okay. Next week, we have Peter Kalm of NYU. So we'll see you then. And thanks, everyone. Have a great week. Bye now.